Problem 13 asks us to find the rate of change of the perimeter. And to start, it gives us a few constants. So first it gives us a constant area of 50 inches squared, and then it also gives us the rate of change of length, which is 2 inches per minute. So one of the first things you want to do when you see a problem like this is identify some useful equations. We have area equals length times width, and we know that to be 50. And then we know the perimeter is going to be 2 times length plus 2 times width. And from here, we want to start to manipulate what we've been given to find that change in perimeter. So to find change in perimeter, one of the things we need is change in width. So we're going to start with, we have dl dt here. And if we integrate this, we'll have our length, and then we can find width from there. So if you find the integral of 2 dt, and this is going to become 2t. And then if we want to plug that into our area equation, this is going to lead us to get a width of equal to 25 over t. And from here, if you take the derivative of this, we'll have a rate of change for width is equal to negative 25 t squared. And this is in inches per minute. And then if we take our perimeter equation, which is P equals 2L plus 2W, and from here, we want to get our change of perimeter equation. So dP dt is going to equal 2 times the derivative of L, which is dl dt, plus 2 times the derivative of width, which is going to be dw dt. And from here, we're going to plug in, and we're going to get 2 times 2 plus 2 times negative 25 over t squared. And this gives us a resultant change in P. A rate of change of P is going to equal 4 minus 50t to the negative 2. Part B asks us to find at what dimensions gives us the smallest perimeter. So to find this, the important thing is we're identifying that we're looking for a maximum, or in this case, a minimum, which is our critical points. And to find a critical point, we have to set a derivative of the equation in question, here perimeter, to 0. Lucky for us, we already have the derivative of our perimeter equation because we found it last in part A. So we get 4 minus 50 times t to the negative 2 equals 0. And then we're just going to go ahead and solve this and find t. All right, as you can see, t equals 5 times root 2 over 2. And so what this is telling us is that at this time interval, our perimeter, which is this equation up here, is at its minimum. But we're not actually asked what that perimeter is. It doesn't matter. We're actually solving for what the dimensions at that perimeter are. So we're looking for L equals 2 times t, and we're looking for W equals 25 t to negative 1. And so if we plug in, we can solve and find that our answers are L equals 5 root 2, and W equals 5 root 2 as well. Problem 14 gives us our first related rates problem. I think the best way to approach these is to identify first any rates that you are given and any equations you think you might need, and then from there, make a path to the rate you're looking for. So first, we are given the change in volume equals 3 meters cubed per minute, and what this is dV dt. We know what we're looking for is dr dt. So if we're looking for dr dt, dv dt can give us the time component of that, which means what we need to find is the radius portion of that, and we need to cancel out the volume part of it. So we're looking for some relationship between radius and volume. So next we want to have an equation with both those components in it, and that's very easy. We know that the volume equation for a cone is 1/3 pi r squared times height. And now This is a good step, but we have height within that, so we need to be able to cancel out height. Luckily, our diagram gives us information that we can simplify with that. So we know that height equals 4 at the maximum and radius equals 2 at the maximum. And because it's a cone, we know that ratio is constant throughout. So we can synthesize that height equals 2 times radius. And we can substitute that in to our volume equation. And we get 2 over 3 pi r cubed. And now if we take the derivative of this, we'll get dv dr 2 pi r cubed, r squared, excuse me. And so right now, we're looking for dr dt, we have dv dt, and we have 1 over dr dv. So if we plug this in, we get dr dt equals 3 over 2 pi r squared. And now the problem is specifically looking for what is the rate of change at a specific height. And so this is pretty simple. dr dt at h equals 2 equals 3 over 2 pi, and if we substitute in our r for h, 1/2 h squared, and then plug in 2, we're going to get 2 pi times 1 squared, which equals 3 over 2 pi as our answer. Number 15 gives us a logarithmic equation and is just testing us on our knowledge of certain rules, logarithmic rules. So the first one, for this problem right here, the first rule that we need to know is the quotient rule, which is just log of any base with a fraction within it equals the log of the numerator minus the log of the denominator. And so essentially what we have here is this problem can then be converted into log base 4 of x plus 1 minus x minus 1 equals 1/2. And then the second rule that we need to know is, I don't actually know the name of this rule, but essentially if you have log base something equals another number, it becomes 4 to the power of the answer equals the body of the logarithm. And then if we solve this, this is 2 times x minus 1 equals x plus 1. And if we solve for x, we're going to get x equals 3. As simple as that. So this doesn't encompass all logarithmic rules, but really what you need to learn about this problem is that you could get asked something as simple as this. But if you don't know all of your log rules, you're going to be left empty-handed. So I would go just Google log rules, and you'll get a nice little picture graph, and just go through and study them. Make sure you're familiar with the product rule, the quotient rule, the power rules. There's a couple different other ones, and just make sure you review those and you know them before going to your exam. Problem 16 asks you to solve and describe how to find 3.4 to the power of 2.1. This problem specifically, I don't think it's the greatest problem there is, but there are two important skills that we want to highlight. First, it's another problem that we can use some of those log rules that we talked about in problem 15, specifically these two rules right here. And we'll get to using those in a second. But I think the more important part of this problem is because it's such a specific number that you'd use a calculator before, and you don't have a calculator on a test like this. I think what it's trying to ask you to do is to observe your approximation skills. So this is my personal opinion on how you would attack this problem. You'd see 3.4 to the power of 2.1, and you'd be able to say, hey, I know 3 to the 2 equals 9, right? And then you'd say 4 to the 2 equals 16. So right now you've been able to approximate that 3.4 to the 2.1 is somewhere between 9 and 16. So whatever your answer is going to be, it's going to be in that range. I think those kind of problem-solving skills right there is more important part of this problem. Now, if you're working off the answer key that I have, it goes use these two rules to simplify into another form, right? So first, we have 3.4 to the 2.1, and using this number raised to the log rule, we can simplify that to becoming e to the ln 3.4 to the 2.1. And now if we use the power rule on just the power of this new form, we can find e times e to the 2.1 times ln of 3.4. And this is about as simple as this problem can get. This is why I said I don't love this problem. The answer key then says you use your lookup table, which is not necessarily something you guys have access to. I'm not sure where this problem was pulled from. And it'll give you that ln to the 3.4 is, oh, I did not look it up. ln 3.4 will give you 1.22. If you multiply these numbers together, which is, again, not something you'll be able to do with a calculator, you'll get 2.562. And then if you solve this, which, again, you will not be able to do without a calculator, you'll get 12.96, approximately, which falls right in our range of 9 and 16. So, again, I want to highlight, I do not like this problem. I don't know where it came from. It's not something you'll be able to do without a calculator. The important parts of it are, again, just a reminder that you should be looking at your log rules and memorizing those rules in case it comes up in a problem or you get a problem like this that might come to an easier solution. And then 2, this is my opinion. This is not something that I was told. I think approximation is an important skill. Again, not necessarily in this context, but you could get some sort of radical or some sort of powered number, and they want to see how you think, and you can break it down maybe in a few more steps than what I just did. But you can. This is definitely something that could happen with radicals and numbers to the power, and they want to kind of see what your, not your guess, but your educated estimate is based on some variables they give you.